Hello and welcome back to the Deep Dive. Great to have you with us again.
Absolutely. Today, we're tackling something really foundational about AI.
Yeah, something we maybe don't think about enough. Like, have you ever stopped to wonder what physically makes AI work? How do these incredibly complex systems actually run?
hmm We hear so much about the code, the algorithms, the brains, as you say.
Right, but there's actual, metal and silicon under the hood doing the heavy lifting,
Yeah.
turning ideas into real operations.
And it's true, looking back at early AI efforts, some of the big hurdles weren't just about the software smarts.
Oh, definitely not.
A huge part of the challenge, as we've seen in the material we looked at, was the limitation of the machines themselves. The hardware, well, it just couldn't do the kind of complex parallel stuff needed to even try and mimic intelligence.
So that's our mission today, really, to unpack that physical foundation. We're going to explore how the hardware powering AI has evolved.
Yeah, looking at how we went from standard computer chips to these really specialized engines built just for AI.
Exactly. Let's dive in. Okay, so let's unpack this. Most AI projects, especially when they're starting out or for a lot of common tasks, they actually begin life running on hardware you'd find in, well, your everyday computer.
Well, or maybe big servers.
Standard CPUs, yeah,
Yeah.
central processing units.
Exactly.
And look, it's important not to downplay them. Modern CPUs, the off-the-shelf kind, they're incredibly powerful compared to what we had, say, 20 years ago.
Oh, night and day.
They give us a great starting point for lots of AI applications. Especially if you're not dealing with, massive data sets or super complex models, they're flexible.
Think about the device you're using right now, maybe listening to us on. Your phone, your laptop.
Mm-hmm.
They all have powerful CPUs inside, running the show, managing everything. They're essential for most computing, and AI often relies on them for the overall control and lots of step-by-step tasks.
And here's where it gets really interesting for AI.
Yeah.
While standard CPUs are powerful, their basic design,
Mm.
it's often based on something called the von Neumann architecture.
Oh, yes. And that design starts hitting some pretty serious walls when you throw really complex, large-scale AI tasks at it. Think training deep neural networks.
The von Neumann bottleneck. I remember reading about this. It's a useful idea, right? Like, imagine
Yeah.
a single, narrow road inside the computer,
Yeah.
and both the instructions what to do and the data what to do. To have to travel back and forth on that same road, one thing at a time.
Precisely. And that single pathway, it just creates a traffic jam, a bottleneck. The processor's constantly waiting for either instructions or data.
Okay.
For normal computing, doing things sequentially, do this, then save that it works, well, reasonably well. But simulating complex stuff, like neural network.
Like the brain, yeah, which isn't just one thing after another.
Exactly. The brain has millions of things happening at once in parallel. Standard von Neumann architecture. It just wasn't built for that kind of massive parallelism that modern AI needs.
That's the struggle.
Massively struggles. Even multi-core processors, which are better, they let you do some things at once.
Right, like having a few workers instead of one.
Yeah, but they still often bump into limits because of how the software has to break tasks down, and they're often still sharing that main path for data. It's like multiple workers sharing the same single toolbox. It gets crowded.
So, okay, for those tasks needing tons of parallel work, they needed something different. Now, interestingly, other ways to design chips did exist, right? Like the Harvard architecture.
Yes, exactly. And that highlights a different way of thinking about how things flow. The Harvard design uses separate paths and separate memory for instructions and data.
Ah, so two roads instead of one.
Pretty much. Instructions travel on one, data on another. This means the processor can grab the next instruction while it's still working with data for the current one.
So it's doing two things at once, in that sense.
Yeah.
Fetching and processing.
Kind of, yeah. It allows for more overlap. Now, while the original Harvard architecture itself wasn't the main thing that revolutionized AI hardware later on, the idea behind it, separating pathways, enabling more simultaneous operations, it really underlines that fundamental need for parallelism that AI brought to the forefront. It showed there were other ways to build chips.
Okay, so standard CPUs hit that bottleneck with AI's parallel needs. Big barrier.
Yeah.
But then, something designed for something totally different steps up and becomes the real game changer for modern AI, especially deep learning.
The GPU graphics processing unit.
Yeah, from video games, right?
Absolutely. Born from the need to render incredibly complex 3D graphics, pushing trillions of calculations per second to make games look real.
All those pixels, textures, lighting.
Exactly. And it just happened that the type of math needed for graphics, lots of matrix multiplication, vector stuff, basically doing the same calculation on huge sets of numbers at once, turned out to be exactly the core math needed for training and running deep neural networks. It was this amazing, almost accidental overlap.
That's the wild part. So why were they so much better at that specific math than a CPU? You said CPUs have a few powerful cores.
Yeah.
What's the GPU setup?
It's the structure. A typical CPU might have, 4, 8, maybe 16 really powerful cores, designed to handle lots of different complex tasks one after another or few at a time.
Right, generalists.
Yeah. A modern high-end GPU, though, it can have thousands of simpler cores.
Thousands.
Yeah.
Seriously, that's, a massive difference.
It is, and the magic is what those thousands of cores do. They're designed to do the same relatively simple math operation, but on many, many different pieces of data all at the same time.
Ah, okay. So less like a few brainy specialists, more like a giant crew of workers,
Yeah.
all doing the same specific repetitive job really fast, but loads of them doing it simultaneously.
That's a great analogy. They take a huge computing job from the CPU, manage their own fast memory, and just crunch through unbelievable amounts of data in parallel. That massive parallel capability, that's what slashed AI training times.
Right, suddenly things that took weeks on CPUs.
Became possible in days, maybe even hours on GPUs.
Yeah.
That shift, driven by hardware originally for gaming, is really what unlocked the deep learning explosion in the 2010s.
That's such a key point. They weren't made for AI, but their design was just what AI needed to break through those old hardware limits.
A truly transformative moment. It showed how hardware built for one thing could revolutionize something else entirely.
Now, okay, repurposing GPUs is fascinating, but the story doesn't end there, does it?
Yeah.
People started thinking, what if we build hardware specifically for AI?
Exactly. Beyond standard CPUs and these powerful but sort of accidentally useful GPUs, researchers and companies started aiming higher, trying to build chips from the ground up, maybe mimicking brains, or just super optimized for AI tasks.
This is where we get into those AI accelerators, right? Or NPUs, neural processing units.
That's the territory. Highly specialized silicon designed purely for AI.
And the material mentions some really ambitious projects trying to build chips based on how the brain is structured.
Yeah, things like IBM's Synapse project, which led to the True North chip. The idea there was really different, trying to integrate memory and processing together, more like biological synapses and neurons. Proper neuromorphic computing.
Wow. That sounds incredibly complex to actually build, though.
Oh, it is. Building totally new chip architectures is incredibly hard, takes ages, costs a fortune. And the material points out a real challenge. Sometimes these really radical novel designs struggle commercially.
Harder to manufacture, maybe? Or get people to program for them.
Could be both. They often struggle against tech that can, plug into existing manufacturing and software systems more easily. Which brings us to things like Google's TPUs, tensor processing units.
Right, TPUs. They're specialized for AI too, but they took off more, didn't they?
They did find a lot of success, yeah. And part of that seems to be because they didn't try to build a completely alien brain-like thing from scratch.
Ah, okay. So what do they do?
They sort of adapted and optimized existing chip design and manufacturing approaches, but they fine-tuned the chip's internal structure specifically for the kind of math AI uses all the time, tensor calculations, the stuff in TensorFlow, especially for running models, inference, and certain training tasks.
So leverage what works, but make it perfect for AI math.
Pretty much. That intense optimization, plus Google needing huge amounts of AI power for their own stuff like search and translation, it made TPUs incredibly efficient for those specific jobs. They were more market-ready, more scalable than some of the really experimental neuromorphic chips.
Interesting. So optimizing existing tech pathways sometimes wins out commercially over starting something completely new and radical, even if the radical idea is clever.
It often seems that way in hardware, yeah. It's a tough balance.
Yeah, just tracing this journey from standard chips hitting that wall, then GPUs kind of accidentally saving the day for parallelism, and now these purpose-built chips like TPUs, it really drives home how deep this field is. The hardware layer is just so crucial.
It really is. None of the amazing software advances could have happened without the hardware evolving alongside it, right? You have to be able to run the calculations.
And if you're finding this as fascinating as we are, sort of peeling back these layers, if you're having those aha moments about how this tech actually works, well, this is exactly the kind of thing we love doing here.
Getting into the nuts and bolts.
Yeah. So consider joining us for more deep dives like this on Channel AI of Think. We're always digging into interesting material, trying to understand how things really work.
So looking ahead then, what does the future of AI hardware look like? Is it just GPUs? Just TPUs?
It seems pretty unlikely it'll be just one thing, right? The future looks hybrid.
Yeah, almost certainly hybrid. CPUs aren't going anywhere. They're still vital for general tasks, running the operating system, orchestrating everything. The flexible brains of the operation.
In GPUs, they'll still be the workhorses for that really heavy-duty parallel math, especially training those enormous models.
Definitely. The heavy lifters for massive parallel tasks. And then we'll see more and more specialized chips, MPUs, AI accelerators, whatever they end up being called.
Tailored for specific jobs.
Exactly. Chips optimized for running AI super efficiently on your phone, or processing sensor data instantly in a robot, or handling specific calculations in data centers way faster, or using less power than a general GPU.
So it's like building a team. A CPU captain, GPU muscle, and then these specialized players for specific roles on the field.
That's a perfect way to think about it. And that combined team, that hybrid approach, is what makes the AI you use every day possible and, increasingly smooth.
Like asking Siri or Alexa a question, that's not just one chip doing that whole thing.
Oh, absolutely not. Think about the chain. There might be a tiny, super low-power chip in the speaker just listening for the wake word. That's its only job.
Okay.
It wakes up the main CPU, which maybe handles capturing your voice and sending it off. Then in the cloud, your voice probably hits servers using powerful GPUs or TPUs for the heavy lifting of speech recognition.
Turning speech to text.
Right. Then that text query might go to other systems, maybe running huge language models on different clusters of CPUs, GPUs, or specialized inference chips to figure out the answer.
Wow.
Finally, the answer comes back, and maybe another specialized chip in your device turns that text back into the voice you hear. It's this whole pipeline of different optimized hardware working together.
That's incredible. Just for one question, it really shows how the hardware isn't just sitting there. It's actively enabling what the AI can even attempt to do.
Absolutely. The material makes that crystal clear. The physical machines are fundamental. Early AI was often limited by hardware, and today's AI is massively enabled by it.
So we've covered quite a journey, from standard chips hitting limits to GPUs providing the accidental key to these new specialized processors emerging.
And thinking about where hardware is going, constantly getting smaller, more powerful, more specialized, maybe embedded everywhere around us. It does make you wonder, doesn't it?
How so?
Well, here's a thought to leave you with. As this hardware gets woven more deeply into our environment, could we see AI capabilities become so integrated, so ubiquitous, that our whole relationship with technology changes fundamentally? Almost invisible, but always there. How might that change things?
That's definitely something to chew on. This deep dive really hammered home that the silicon matters just as much as the software. Thanks for joining us for this exploration. Hope you got some new insights.
My pleasure. It's fascinating stuff.
Join us next time as we dive into another topic from the sources we explore. If you enjoyed this, learned something new, maybe share it with a friend or colleague who's curious about AI.
Good idea.
And hey, don't forget to subscribe to channel AI of Think so you catch our next deep dive. Thanks for listening.